In this video, we're going to discuss simple ligand exchange mechanisms from 6-coordinate species and 4-coordinate species. What we're first going to do is we're going to distinguish between a compound that is kinetically inert versus labile. When we talk about whether or not something is kinetically inert or kinetically labile, we're talking about the lifetime of a species with respect to ligand exchange. Let's set up a reaction where we have a metal 2 hexaaqua species, and we're just looking at the exchange of one of those waters. This will have some rate constant associated with it. And we've replaced one of those waters with bulk water from solvent. We can define the average resonance lifetime for one of those waters on that metal site with the symbol tau, which is related to K by 1 over K. In general, if tau is greater than 10 to the 1 per second, we say that the species is kinetically inert, but if tau is less than 10 to the 1 per second, then we say that the species is labile. And the shorter the lifetime of water on that metal center is, the more labile that complex is. We can look at some general trends with this ligand exchange, and what we find is that for the same dN count, the higher the charge on the metal center, the longer tau is, or the more kinetically inert the compound happens to be. If we look down a column in the transition metals, what we find is that first row metals or more labile than second and third row metals. And finally, crystal field stabilization energy seems to give some insight into whether or not a compound is going to be kinetically inert versus kinetically labile. So if you look at the change in crystal field stabilization energy, if you have a positive change upon, for example, going from a 6-coordinate to a 5-coordinate species in the case of a dissociative mechanism, or a 6-coordinate to a 7-coordinate species in the case of a associative mechanism, then this is going to correlate with a negative change in the overall enthalpy upon going to that transition state, which is going to lead to a more kinetically labile species. If we examine tau for the water exchange for your first row M2 plus hexaaqua species, what you find is that vanadium 2 plus is the most stabile, followed by nickel 2 plus, cobalt 2 plus, iron 2 plus, manganese 2 plus, zinc 2 plus, chromium 2 plus, and copper 2 plus. And if you go through and you calculate the change in crystal field stabilization energies, what you, upon going from 6-coordinate to 5-coordinate or 6-coordinate to 7-coordinate, what you find is that These metals down here have the most negative change in crystal field stabilization energies, meaning that you're going to have the most positive change in delta H double dagger, so a high activation barrier, while these metals down here have the most positive change in crystal field stabilization energy upon going from the 6 coordinate to the 5 coordinate or 7 coordinate species. So those have the lowest delta H double dagger. We're now going to briefly examine ligand substitution reactions at 6 coordinate metal centers. So we're looking at this reaction. Where Y is coming in and displacing ligand X. If we look at the dependence of this reaction on the MX species, the general rate goes in the order of hydroxide having the slowest rate for the reaction, followed by azide, which is approximately the same as thiocyanate, which is followed by acetate, followed by chloride, bromide, iodide, and then finally nitrate, if we have this series of ligands. Essentially, the rate depends on the metal-ligand bond strength, where the stronger the MX bond, the slower the reaction. Another finding is that at high concentrations of the incoming group Y, is independent of your concentration of Y, or the type of ligand that's being bound to it. However, at low concentrations of Y, the rate depends on the nature and the concentration of Y, as well as the complex that you're starting with. The first two observations seems to be consistent with the dissociative type mechanism, where you would lose X, forming a 5-coordinate species, and then Y would come in and occupy its place. While in contrast, the third point seems to be consistent with an associative type mechanism, or an IA type mechanism, where you form a 7-coordinate species followed by the displacement of X. A mechanism that's consistent with all of these findings was developed by N. Wilkins, and it's known as the Eigen-Wilkins mechanism. In this mechanism, it's say that there's a pre-equilibrium that involves the formation of a so-called encounter complex. Where Y is contained in a very close space relative to the ML5X. So you have this encounter complex where Y is associated with the 6-coordinate species. You then lose that ligand X, forming a 5-coordinate compound, and Y is right there to come in and bind to that metal center. Most 6-coordinate compounds undergo this type of mechanism under ligand substitution, where you form this encounter complex. But for the most part, you can think about this as following a D, a dissociative, or an ID, a dissociative interchange type mechanism. We're now going to briefly discuss the stereochemistry of ligand exchange at 6-coordinate metal centers. So let's say that we have our ML5X plus Y going to the ML5Y plus X reaction. And as we said, this follows a dissociative-like process. So starting with that, I'm going to label one of those L ligands just so we can follow it. We have this species, which is going to lose that X ligand. Forming this square pyramidal compound. If the association of Y is rapid relative to a Berry pseudorotation, then you're going to retain the original stereochemistry. And Y is going to substitute trans to that L star ligand. However, if a Berry pseudorotation is rapid, then you would undergo conversion from the square pyramidal to the trigonal bipyramidal, back to the square pyramidal, and now we have the vacant site cis to that L star. So Y can come in and occupy there. Forming the cis species. So depending upon the speed of this Berry pseudorotation, you'll either get rapid association of Y, forming exclusively this trans product, or you go through a rapid equilibrating Berry pseudorotation and you'll get a mixture of both the cis and the trans species. So the product distribution is going to be highly dependent upon the nucleophilicity of Y, coupled with how readily that complex will undergo the Berry pseudorotation. We're now going to talk about ligand exchange at 4-coordinate square planar metal sites. In these cases, these almost exclusively go through associative type mechanisms. So we're going to look at the reaction of platinum, square planar platinum 2 compounds displacing an X ligand for a Y ligand. The mechanism, as we said, goes through an associative type process. So you have your four-coordinate platinum 2 complex. Y comes in, forming your 5-coordinate complex in the apical position. This undergoes a Berry pseudorotation. So a Berry pseudorotation, forming your trigonal bipyramidal compound, which then goes back to a square pyramidal compound, but now X is in the apical position. and then you lose that axial ligand. Forming this species. The majority of these reactions are what we call stereoretentive. What we mean by this is that Y will go in the same ligand position as X relative to all the other ligands. So if we're to label this L ligand trans to that X, what we find is that ligand stays in the same place throughout this process. And it turns out that this trans ligand is what dictates the ligand substitution reaction. And it's dictating the ligand substitution reaction by displacing the ligand trans to it, that X ligand. It does this through both a trans effect and a trans influence. Trans effects versus trans influence both apply to the influence that a ligand has on another one trans to itself. A trans influence is a ground state effect. If we have some platinum complex, sticking with platinum, and we're looking at this trans platinum X bond, the longer that L ligand makes that platinum X bond relative to other L ligands, the stronger we say it's having a trans influence, the stronger the trans influence, and hence the weaker the bond. What influences the trans influence is the sigma donor ability of the L ligand. The stronger the sigma donor, the more it's going to have a trans influence on the ligand trans to it. This is because both the L and the X ligand are making bonding and anti-bonding combinations. The stronger of a sigma donor you have, the higher in energy that anti-bonding combination is going to become. So it's going to impart a weakening of that trans platinum X bond. The trans effect is a purely kinetic effect. It describes how rapidly that X ligand will dissociate from that metal site in response to having that ligand trans to it. And the trans effect goes in the order of water being approximately the same as hydroxide, which is approximately the same as an amine ligand, which is approximately the same as a pyridine ligand, followed by chloride, bromide, iodide, which is approximately the same as NO2 minus, followed by methyl, phosphines, and then way off the scale as far as having a very strong trans effect are COs, cyanides, and alkene ligands. So as we see, what really creates a strong trans effect is a ligand that has these pi acceptor type orbitals. Pi acceptors promote ligand association trans to that particular ligand. The reason for this has to do with how the ligand-based p-type orbitals are interacting with the metal pi-type orbitals in the trigonal bipyramidal intermediate during the Berry pseudo-rotation. To understand this, we're going to look at this particular reaction. So labeling our ligands. We have this. We then form the 5-coordinate square pyramidal complex followed by the Berry pseudo-rotation. And when we do the Berry pseudo-rotation, going to the trigonal bipyramidal species, that L3 ligand, along with the X and the Y ligands, are going to remain in the equatorial plane. So the L1 and L2 are remaining trans to each other, and the L3, the X, and the Y now form your equatorial plane in the trigonal bipyramidal species following the Berry pseudo-rotation. This then forms your substituted complex. We're going to look at the orbital interactions in our trigonal bipyramidal intermediate, where we have our L ligand here, which is our trans director, which, as we said, when these are pi acceptor ligands, they form strong trans directors. They display a strong trans effect. We have the metal, which has electrons associated with that particular d orbital, and these are donating into that p orbital. They're accepting electron density from the metal center into that empty p-type orbital. You have these X ligands that are here. And if these are pi donating ligands, they can donate electron density into that now deficient metal d-type orbital. So it's this electron withdrawing effect here coupled with this electron donating effect here that's keeping the X and the Y ligands in this equatorial plane. So upon doing the Berry pseudo-rotation, this X ligand will be trans to L3, or the Y ligand will be trans to L3. So you can go back this way and just regenerate the starting material, or go this way and form product. In both cases, you're going to be positioning that ligand trans to L3 because of this pi directing effect. This can be used in the production of specific isomers of metal salts. So for example, let's say that we wanted to make this particular platinum complex. It's given an overall minus charge. Well, you could start with platinum tetrachloride and then convert it into, for example, the platinum phosphine compound. Now, when you add in a cyanide ligand, this is going to add but it's going to add trans to the ligand that has the strongest trans influence, which in this case is that phosphine ligand. So you would end up generating this species upon the displacement of a chloroligand with the cyanoligand.